Hi, we're at the secret Oakland Raiders headquarters in Alameda, California. The Raiders come here to practice and strategize for their upcoming games. But we're here today to do some... Whoa! Carpool Chemistry. Today, we're going to be drawing Lewis structures with double bonds and resonance. Let's say, for example, we have sulfur dioxide, SO2, and we're asked to find the Lewis structure. Well, we could write that in the skeleton structure in different ways. Skeleton structure possibilities. This could be written as sulfur, oxygen, oxygen, or it could be written as oxygen, sulfur, oxygen, or it could be written as O, O, S. Which one of these is the best way? Well, as we know from our notes, oxygen atoms are usually bonded to a central non-metal atom. That means oxygen wants to be on the outside, as we see right over here. So let's put oxygen on the outside, O, S, O. Now the question is, do we have enough outer shell valence electrons to make this happen? That is, the valence electrons are the pieces of glue that hold this together. In order to find out, we need to draw our electron tabulation. And of course, these are the valence electrons, or the outer shell electrons. Let's take a look at oxygen. Oxygen, there are 2 atoms times, and each oxygen has 6 outer shell valence electrons. They're in main group 6, for a total of 12. Sulfur has, there's 1 atom times, and sulfur also has 6 outside valence electrons. 6 valence electrons is equal to 6, for a total of 18 valence electrons holding the structure together. Is that enough? Well, we need to deduct or take away 2 electrons for each of these single bonds, because that's what it takes to make those. So single bonds, 2 bonds times 2 electrons per bond. So we use up 4 of our electrons by forming these single bonds here, leaving us with 14 remaining. Well, let's take a look at the oxygen. We see 2 valence electrons associated with it. It wants a total of 8 to have that stable octet configuration, so it needs 6 more. Do we have 6 more? We sure do. We have 14 more. 1, 2, 3, 4, 5, 6. Oxygen now is satisfied as far as electrons go. 14 minus 6, so we used up 6 for that oxygen. Let's take a look at sulfur. Does sulfur have enough electrons? It's got 2 from this bond plus 2 from that bond. It needs a total of 8 to be stable, so that means it needs 4 more. Do we have 4 more in our stash of electrons down here? We sure do. So let's go ahead and put those in. 1, 2, 3, 4. And let's take that into account. Down in our tabulation, we used up 4. This is like accounting. 8 minus 4 is 4. 4 left over. This oxygen over here has 2. It needs a total of 8. That means it needs 6 more. But do we have 6 more to give to it? No, we don't. We only have 4. So let's at least give it those 4. 1, 2, 3, 4. And we subtracted it down over here, leaving us with a 0. So these are all the electrons that we have to work with. It's still not enough. So what does oxygen say to sulfur if they could speak to each other? It says, hey, I need more electrons. Can you share one with me? And sulfur says, yes, I'll share one with you. So they share an electron, creating another bond. Sulfur now has 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. one too many. Oxygen now has 1, 2, 3, 4, 5, 6, 7 electrons. One too few. So sulfur goes ahead and gives oxygen. Well, it doesn't really give, but we're going to reposition one of the electrons from sulfur onto the oxygen. So I'm going to go ahead and erase this electron over here. I'm going to reposition it over there. Okay, so this arrow will indicate that, hey, we got that electron from there. And now oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Sulfur also has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And we are now stable. If you want to clean that up, you can go oxygen with 6 electrons around it with a single bond, sulfur, and these two lines here represent a double bond with the oxygen. Sulfur would have 1 electron, 2 electrons there. Oxygen has 1, 2, 3, 4. So there's our Lewis structure for sulfur dioxide. Now, as it turns out, because the oxygen's here and we have another same element, oxygen over here, this double bond could just as easily have gone to this sulfur-oxygen connection right over here. As it turns out, scientists have found that in this structure over here, although you might think that there would be 2 different bonds, they have found out that there's only 1 bond. And it's somewhere in between a single bond and a double bond. It's called resonance. To draw a resonance structure, you draw the structure again. Let's draw a double-headed arrow, resonance. And you draw the structure again, but this time, instead of having the double bond on the right oxygen, you have the double bond on the left oxygen. And then you fill in your remaining electrons. 1, 2, 3, 4 for that side, 2 for the sulfur still, and 6 electrons for the right-hand side. And what we're saying with resonance is that that double bond could either be on the right side or on the left side, and it's just as equally probable. So what happens is that double bond actually shifts between the two really fast. It goes boom, 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 back and forth, back and forth, back and forth. It resonates, just like this eraser over here. Where is this eraser? It's right there. Then it's right there. There, 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 there. Or it could be there, all over the place. It is resonating, just like plucking a string on a guitar. So that's how you draw Lewis structures with double bonds and resonance structures. From the Oakland Raiders headquarters in Alameda, California, this is Carpool Chemistry. Thanks for watching.